Welcome to this explainer. Today, we're diving deep into the incredible and honestly often invisible materials that are literally shaping our modern world. Specifically, we're going to focus our attention on really understanding the physical properties and the real-world applications of polymer matrix composites. We interact with these things constantly, but rarely do we actually stop to appreciate the brilliant engineering hiding just beneath the surface. To kick things off, I want you to consider the seemingly impossible physical properties required to achieve some pretty monumental engineering feats. For instance, how exactly do you build an advanced aircraft that just evades radar detection? Or, on a more grounded level, how do you construct a marine boat that can withstand decades of harsh saltwater exposure without ever rotting or corroding? These are massive, demanding challenges. Standard materials, they just can't handle it. The answer to these challenges doesn't lie in traditional heavy metals, but in a class of highly engineered supermaterials known as polymer matrix composites. Think about the sleek surface of a stealth aircraft. That structural integrity, that specialized surface functionality, it's achieved precisely because materials engineers have completely reimagined what materials can do, right down to the molecular level. So here's our exact flight path for this explainer. First, beyond basic plastics. 2. Introducing polymer composites. 3. Blueprint of a composite. 4. High-tech applications. And finally, 5. Why composites matter. All right, section 1. Beyond basic plastics, the limits of traditional polymers. To really appreciate the power of composites, we first have to acknowledge a simple truth. While basic single-ingredient polymers are incredibly useful, they've got strict physical limitations when we throw them into extreme environments or under heavy structural loads. But, even before getting to full-blown composites, engineers start overcoming those limits by combining specific ingredients. It's kind of like a master chef balancing a flavor profile. When engineers synthesize a copolymer, say moving from standard PVC to PVDC, they drastically upgrade the base material's fundamental properties. Because PVDC has 2 chlorine atoms attached to the same carbon atom on its vinyl chain, it gets this highly symmetrical structure. This brilliant little molecular tweak gives it much higher crystallinity, way more structural strength, and vastly superior resistance to water absorption and chemical attacks compared to standard PVC. So whether engineers are mixing flexible PVC with rigid PVC to create a tough new blend, or combining polycarbonates with ABS plastics, which is acrylonitrile butadiene styrene, by the way, the ultimate goal is always exactly the same. They are trying to literally engineer away the inherent flaws of the base material. You keep the best properties of the individual components, and you use them to support and cover for each other's weaknesses. Moving on to Section 2, Introducing Polymer Composites, the ultimate engineering solution. Okay, so sometimes simply mixing or blending 2 polymers together still just isn't enough for the most demanding, heavy-duty industrial needs. When simple blends fall short, that's when we turn to polymer matrix composites. A composite is essentially a system. It consists of a primary polymer base, we call that the matrix, which is then physically reinforced with a secondary, entirely different element. We're talking about embedding things like continuous glass or carbon fibers, microscopic short whiskers, or even heavy woven fabrics directly into the plastic. By doing this, we create a highly specialized composite that behaves completely differently. It's exponentially stronger than the standard plastic on its own. Section 3, Blueprint of a Composite. Architectural layouts. To really grasp how these properties are achieved, we've got to zoom into the microscopic architecture to see exactly how these physical reinforcements are arranged inside the polymer matrix. There is massive variety in composite design. Simple particulate and mineral blends, well, those might be used to increase hardness or just reduce cost. But things get really advanced with reinforcements made of continuous fibers pulling in one single direction, highly complex woven fabrics that look almost like heavy textiles, and even stacked, layered composites. The physical layout literally changes everything about how the final material performs. And get this, even when using tiny, short, discontinuous fibers, what engineers casually call whiskers, absolutely nothing is left to chance. These short fibers can be randomly distributed throughout the matrix if the goal is just to increase the material's overall all-around toughness. But if an engineer knows exactly which physical forces the material is going to face in the real world, like, say, a huge pulling force from one specific direction, they can meticulously align those microscopic fibers to directly counteract that targeted stress. It is incredibly precise. Section 4, High-Tech Applications, From Theory to Reality. All right. Now that we understand the structural theory and the actual properties at play, it's time to bridge the gap between those microscopic blueprints and tangible reality. Take those raw woven reinforcement materials. They look almost like rolls of colorful, heavy netting, right? Well, when they're embedded into a polymer matrix, they transform directly into massive, heavy-duty industrial pipes boasting immense structural strength. Because of the composite structure, these pipes remain highly resistant to water and chemical corrosion, all while handling extreme, intense pressure. And it doesn't stop there. These exact same composite principles allow us to conquer the oceans. Looking at sleek marine boats, you're basically seeing polymer matrix composites in their natural habitat. Think about it. Traditional wood rots, standard metals rust, and they're incredibly heavy. But by molding a polymer base and reinforcing it with structural fibers, engineers can create a boat hull that is super lightweight for fuel efficiency, insanely strong against crashing waves, and completely impervious to the rotting effects of a harsh marine environment. But the applications go way, way beyond heavy industry and transportation. We rely on these materials for automotive parts, like carburetor covers. We use specialized nonstick coatings on technical and household tools. We even safely insulate high-frequency and high-voltage electrical cables thanks to their excellent dielectric properties. We use these composites to formulate highly abrasive resistant floor tiles, tough road marking paints, and incredibly durable coatings for your travel luggage. They're absolutely everywhere. Which brings us to Section 5, Why Composites Matter, Engineering the Future. Understanding the fundamental properties and applications of these materials isn't just some academic exercise. It's the vital, foundational step we need to push the boundaries of modern design and solve tomorrow's problems. The ultimate goal of any materials engineer, or honestly anyone looking to innovate in product design, is to master a specific progression. First, you've got to deeply understand the basic properties of raw polymers. Second, you analyze the extreme structural or environmental demands of your intended application. Basically, what forces will it face? What harsh chemicals will it touch? And finally, step 3, you synthesize and select the precise polymer matrix composite layout, whether that's continuous fiber, woven, or particulate, to perfectly fulfill that exact physical requirement. It's like a brilliant, high-stakes logical puzzle. So I want to leave you with a bit of a provocative thought. Look around your room right now. Seriously, take a second and look. View your everyday world through the eyes of a materials engineer. Which standard, heavy, or easily broken items sitting right around you could be drastically improved, lightened, or fundamentally strengthened if they were completely redesigned using the advanced polymer matrix composites we explored today? Once you start seeing the world in terms of matrix materials and precise structural reinforcements, you really begin to imagine just how much further we can push the boundaries of design. Thanks so much for joining me on this explainer, and remember to keep questioning how the world around you is built.